All right, we've covered PCA and LDA, both of which are powerful tools for simplifying and understanding your data. But let's face it, sometimes the data you're working with doesn't follow the rules. It's messy, nonlinear, and doesn't fit neatly into categories. You know there are patterns hiding in there, but they're buried in a jungle of dimensions. This is where T-Distributed Stochastic Neighbor Embedding, or T-SNE, shines. Imagine you're an explorer venturing into an uncharted jungle. You have no map, no guide, just a sense that somewhere out there are hidden villages and treasures to discover. But how do you make sense of the chaos around you? T-SNE acts like a magical compass, taking your high-dimensional data and unfolding it into a map you can actually read. It doesn't just simplify the data, it reveals the hidden structure within it, showing you where clusters, patterns, and outliers lie. Here's how it works. First, T-SNE starts by creating a high-dimensional neighborhood map. It looks at the relationships between data points, how similar or close they are, and turns that into probabilities. Think of this as grouping people based on their friendships. If two people are close friends, they'll be grouped together. If they're distant acquaintances, the connection will be weaker. T-SNE captures these relationships at a local level, ensuring that the fine details of your data aren't lost. Next, we set the perplexity parameter, which is like deciding how big each neighborhood should be. Should we focus on just the closest friends or zoom out to include a larger social circle? A lower perplexity value zooms in on the local structure, revealing fine details and tight-knit clusters. A higher value takes a more global view, showing how groups relate to each other on a broader scale. Choosing the right perplexity is key. It's a balance between seeing the trees in the forest. Then, T-SNE gets to work using gradient descent optimization. This is where the magic happens. It takes the high-dimensional relationships from the original data and tries to recreate them in 2 or 3 dimensions. But here's the catch. The goal isn't to perfectly match the original data. Instead, T-SNE prioritizes preserving the local structure, ensuring that points that were close together in high dimensions remain close in the new lower dimensional space. Through iterative adjustments, it fine-tunes the positions of data points until the map is as accurate as possible. The end result? A beautifully intuitive visualization. T-SNE doesn't just flatten your data, it transforms it into something you can actually see and understand. Clusters that were hidden in the chaos now stand out clearly, revealing groups, anomalies, and relationships that would have been impossible to detect otherwise. So, where does T-SNE shine? It's an incredible tool for exploratory data analysis. If you're working with datasets like social networks, genetics, or customer behavior, T-SNE helps you uncover insights that might otherwise stay hidden. For example, in bioinformatics, it can reveal clusters of genes with similar expression patterns. In fraud detection, it can identify outliers that don't belong. And in social network analysis, it can map out communities and influences with stunning clarity. But here's the thing. T-SNE isn't perfect. It's computationally intensive, so it might not scale well to extremely large datasets. And because it focuses on preserving local structure, it might not always capture the global relationships in your data. That's why it's often used alongside other dimensionality reduction techniques like PCA. So what's the takeaway? If PCA is your analytical workhorse and LDA is your classifier, T-SNE is your storyteller. It transforms complex, high-dimensional datasets into clear visual narratives. But remember, choosing the right technique isn't just about what's powerful. It's about what fits your data and your goals. And speaking of choices, how do you decide when to use PCA, LDA, or T-SNE? That's exactly what we'll dive into next.